Okay guys, let's take a look at today's lesson. Today we're going to be working on another calculus concept where we actually estimate the area under a curve. Okay, so we're just working on, it's called a Riemann sum. Actually, these rectangles are Riemann sums, and we're just going to work with just two of the types of Riemann sums, the right rectangles and the left rectangles. So let's look and see what's going on. One of the basic problems of calculus is to find the area under the curve. That's integration. And the area between the curve and the x-axis right here is what we're going to be focusing on. And here's an example of right rectangles. The n value stands for the number of rectangles that are being used. N is 15, so there are 15 rectangles. These are right rectangles, and the reason they're called right rectangles or a right Riemann sum is because the right corner of the rectangle is the part that is touching the curve, touching the function. So if we were to calculate the area of this rectangle, what we would do is we would get the function value at that point, whatever that happens to be, the function value at that point, and multiply it by this width. So it would be this value, this function value, times the width. And that's basically how we do this. We just find the area of each of the rectangles and we add them up. So right rectangles, see the right corner is on the function, no matter which way we're headed. Left rectangles is because the left corner is on the function. And so if we were going to calculate the area of one of these, we would calculate this distance right here. It would be this function value. And then we would multiply it by this width, whatever that width happens to be. That would give us the area of this one rectangle. And then we would do the area of each one and add them up. So that's basically how we get estimates of area, is we use this technique called Riemann sums. So there are going to be some important concepts that have to do with this regarding underestimates and overestimates. I think that you can tell by the graphs that let's look at our when would we get an underestimate. So notice right here on this part of the curve, all the rectangles are underneath the curve. Okay, let's see if we can find some patterns here and see on the decrease. So what that means is if we have a decreasing function, with right rectangles, that would give us an underestimate. Let's see what else. So let's see where else we can find some kind of holes. Right here, if you look at this part right here, this is an increasing function. See, there's spaces right here. So this would constitute our calculating these areas. We would be leaving out some chunks of area. And so that would be the case here. And so on an increasing function, with left rectangles, that would give us an underestimate. Now let's look at the situations where we would get an overestimate. Okay, so let's start with our right rectangles. Look at this part right here. See how we're increasing along here? We have an increasing function and we're using a right rectangle. Notice how there's a bunch of portions of the rectangle sticking up above our curve. So that would be a situation that we would get an overestimate if we had an increasing function with a right rectangle. And another situation, let's look on the left rectangles and see where we can find that. Here, if we see right here, this function is decreasing and we have some extra area right here. So if we are using a left rectangle we have a decreasing function with a left rectangle. So these are some things that you don't necessarily have to memorize. If you can just draw it out, you can really look and see, well, what's going on? Am I going to have too much area, or am I going to have not enough area? And that will lead us to our answer of this question. It's a typical question that we get in calculus, is our estimate, is it an underestimate or an overestimate? Alright, so let's look at some examples. Let's do a few examples of using these Riemann sums. So the first one, we're asked to approximate the area under the graph of 1 over x, and they actually give us the graph. No, they don't normally, but that's kind of nice. They give us the graph. And they want us to go from 1 to 5. It's kind of hard to see these numbers, but this is 1, 2, 3, 4, and 5. Okay, so we're going to approximate the area from an x value of 1 to an x value of 5 using n equals 4. N equals 4 means I'm going to have 4 rectangles, so I would have to divide this space up evenly into 4 rectangles, just nicely. They're all 1 width apart. And we're going to use right endpoints. Okay, so let's start with that. We're going to use right endpoints. So if this is my first rectangle, and I want the right side of the rectangle to be touching the curve, then I'm going to draw my rectangle like this. Okay, that's my first rectangle. And again, we're using right endpoints or right corners. There's a lot of different ways to refer to that, but it's just the right part of the rectangle is going to be actually touching the curve. Okay, so I'm just drawing in the rectangles. It just kind of helps me. I'm real visual, so it helps me to get a picture on what in the world's going on. So in order to calculate this area, this is actually a typical AP problem where we have to find approximate area under the curve. We have to show, to get points, we have to show our work. We have to show the products and the sums. So in other words, how am I going to get the area of this particular rectangle? I'm going to take my height, I'm going to take this distance right here, and I'm going to multiply it by this distance. I mean, that's how we find areas of rectangles, right? That's really all there is to it, is just finding the area of each rectangle. So this rectangle right here, this height is the function value at 2. So it's f of 2 times the width, which is 1, plus. For this particular rectangle, it's the function value. See, this function value right here is at 3 times the width of 1, plus. For this rectangle, the rectangle touches right here where the function value is 4. So f of 4 times 1 plus, and this one would be f of 5 times 1. So this is a demonstration of showing the products and the sums. That is a required step. So once we finish the products and the sums, we could go straight to the answer if we had a calculator. That'd be fine. We don't have a calculator right now, so we're just going to do them one at a time. So I would take the 2 and I would substitute it in here. So f of 2 is 1 over 2, and 1 over 2 times 1 is 1 over 2. Okay, so do we see where we get these function values from? I'm just going back to the function, and I'm plugging in a 3. So it'll be 1 over 3 times 1, which is 1 over 3, plus, I'm going to go back and plug a 4 in, 1 over 4 times 1, which is 1 over 4, and 1 over 5 times 1, which is 1 over 5. And then with the calculator, we could add this up fairly quickly. It's 77 over 60. So that's my estimate using a right Riemann sum or right endpoints. And now the question is it an over or underestimate? When we answer the question, we can tell from our graph, that it's an underestimate, but we can't use that in our justification. We need to write a justification. We're training for next year. So we can't say, oh, well, there's space left. That's not mathematical. What we do is we say that it is an underestimate because we have a decreasing function with right endpoints. And that's our reason. Okay, it's an underestimate because we have to say why. Because it's a decreasing function with right endpoints. We just looked at that. We went over that in pretty much detail on the last slide. about when you would have an under and over estimate. Okay, hopefully that's okay. Now, on the AP test next year, it's not really customary for us to have nice even intervals like this. So I wanted to throw in a problem where we didn't have even intervals. That would be problem number 2. So we're going to use left rectangles to approximate the area under the curve of f of x from 0 to 10. So if you can tell, these increments are not even. I have 2 spaces between these x values, 3 spaces, and so it's just not even. So what I like to do, you don't have to, but I like to draw a picture. That really helps me visually. So I'm going to just plot these points, and then we're going to investigate it just kind of piece by piece. I'm going to plot the points. So I have 0, 2. So that's that point. And then I have 2, 3. That right there. Then we have 5, 5. So 5, 5, round in there. 7, 7. And 10, 8. Okay, so these are the data points that were given. Now, what we need to do, we aren't told how many rectangles, but we really don't have many choices. I hope you can see, I can have a rectangle in this space, 1 in this one, 1 in this one, and 1 in this one. So I'm going to have 1, 2, 3, 4 rectangles. They're basically given to us by the amount of data they give us. That's what we have to do. We have to use the data they give us. We can't make up stuff or average things. It's not a thing. We just use the points that we're given. And we want to use the left side of the rectangle. So if I'm forming a rectangle right here, and I want to use the left side, I'm going to have to use this point right here. That's the left side of my rectangle, and then I would draw it down here. So we're using left points. So for this rectangle that's in this space, I'm going to use this. Let me just draw this line down here. I'm going to use this left side. And for this rectangle in this space, I'm going to use this left side. Okay. And then for this rectangle, I'm going to use, again, the left side. And we can see that this poor little guy is left out. We don't use this one at all. Okay. So now let's write our products and sums. So we can just take the products and sums off of each rectangle. So let's work on this one. I have a height of 2 and a width of 2. Plus, I have a height of 3 and a width of a width of 3. Plus, I have a height of 5 and a width of 2. Plus, my last rectangle, I have a height of 7 and width of width of 3. And so those are my products and my sums. Those are the answers. Now, if we have a calculator or if we can do it in our head, we just go straight to the answer. It'll be fine. Or we can show the intermediary work. It's really up to you, but this is required. So we have 2 times 2, which is 4, plus 3 times 3, which is 9, plus 10, plus 7 is 21. We add all that up, and we get 44. Okay, so there is our estimate. Now notice they're not asking us about over or underestimate on this because we really don't know what the curve looks like. We don't, I mean, it looks like it's increasing the whole time, but we really don't know. So they're not going to ask us that question on something like this. They'll ask us that question when we have an actual curve that we can see that's either increasing or decreasing, is when they'll ask us about the over underestimate thing. But this one, we're pretty much have our estimate right here of 44. All right.